Okay, explaining a question I did quite a long time ago as well for functional programming. So for this question, it says we're concerned with a particular stable sorting algorithm with its implementation as a function. And when we have a sort and then a sort equals merge all runs, which is a composition of two functions that you will be asked to define. Basically what we have is a run is a list to be sorted in a contiguous non-empty segment, which is already in ascending order. The composition first divides the input into runs and then combines all these runs by merging them without changing the order of equal elements. For part A, we're asked to write an implementation of merge all, which is of type, has property order A, and then takes a nested list of A's, and then outputs a table of A's as a call Fodor, the Fodor list. Okay, so essentially what this algo is doing in simpler terms is that it's going to first have an array, something like this, and then what it does is it first kind of cuts it into pieces that are already in ascending order. So like let's say it was these this, and then it just combines a merge so that you have a merge sort of these what we call the segments as we call them runs. So that's the idea behind that. So we're first going to write the merge all. So we just have the runs and combine them together. So we're just going to call the, like basically the standard function of merge, and that's kind of what we're going to do. So merge all is just going to be the folder of merge of an empty list. Yeah. And then because if you're kind of thinking about how to merge the things, right, we're just going to call recursively call down the merge. So the idea is that, for instance, here, what we're going to do is we're going to first combine, if we're calling this 1, 2, 3, 4. How we're going to do it is we're going to first merge 3 and 4 together, then the combined product of the 2, 3, 4, and then the 1, 2, 3, 4 together, right? And then just merge it together. So we're just going to call the folder with the merge function of the empty list. And then the merge is just basically standard bookwork. It has order A, and then we take a list of A's, a list of A's, and outputs a list of A's, right? And then what we have is if we're just going to pattern match, right? If we have such a thing, x of x's, y's of y's. Um, if x is smaller than or equal to y, then we're going to do basically x merge x is y, y is right. We're just going to take the x and put it in front. If y was a bigger element, like the smaller element, then we would just put y in the front and do this. And then if it was an empty list, we would just pop the rest in. If it was the empty list on the other side, we just pop the one that's remaining on the end. So that's just the definition of merge, and I think part A is pretty straightforward. For part B, we're asked to write out an implementation of runs of order A to A to A as a call folder. So what we do for this is that each run should be as long as possible. So for instance, run sacrilegious would be split in this way, right? So the runs in ascending order. So yeah, we're going to try to write this that part in terms of folder. So we would have runs of order A and it goes to this. And then we have the folder add of this. And then if we're trying to add something, right, we're going to define our own function add. We're going to define it this way. So we're just going to take two inputs, x and x's, right? And then we're going to check the condition. If it's the first kind of the first element of the thing when it's no, so like there's nothing in it, we're just beginning, then we're going to insert it, right? Or otherwise, if x is the head of y's. So the idea is that if x was this current element is out of order and we have to start a new one, then the idea is that we start a new one with x and then we have x's um, is equal to that. Otherwise, we would just insert it at the front, right? So then it would just be x of y is y's. So basically, we split the x's into y's and y's. So the idea is that we have something of this form. So it would just be x, y's, ys, y, S, S. Where basically we're just gonna compare, okay, this is one list, right? This is a nested list where there are many Ys of the runs. So we're just going to compare if the head of this Y's, X is smaller than this head, then X would have been belonging in this, right? So then we could have done that. Otherwise, what we would do is we just kind of pop it in, like if it fits, then we just have like inside. Otherwise, we kind of just create X as our own thing. And then, yeah, we just split it up like that. So that's it for part B. Part C, we're asked to estimate the worst case complexity of the function runs, merge, draw, and sort as defined above in terms of the list to be sorted. So for this, what we have would be something like this. The add function is pretty straightforward, right? We just kind of compare the case and then just add it in. So it takes complexity O1 because we're just consing it, so it doesn't add much complexity. For the runs program, what we do is we have to go through the list, right? We have to iterate through from one end to the other. So hence it would be O(n). For merge all, it would be O(n) squared in the worst case scenario because the worst case would be when it's descending, right? So then all of our runs would be just elements of one. So then that means that we're going to have to every time go through the whole thing and then find the one that's smallest to be added. So then that would just be a n squared algo because every time we have to go through this and then there's n elements to it. So then it would be n squared. And sort would just be running all of these together. So the worst one out of this is merge all, so the sort complexity would take the same. So that's for part C. For part D, we have is the complexity of this implementation of sort asymptotically optimal? If not, suggest how to improve the asymptotic complexity without changing the value of runs and merge all. So something we can realize from earlier that we were talking about is the idea of merge sort, right? We're basically implementing merge sort. Like we want to merge something together. So the ideal situation is if we have these runs, right? We will want to combine the runs together into kind of like sections and then combine it so that we have a total of log n rounds. But in reality, what we're doing with the fold R as of now is basically, okay, we're going to have one, then we're going to combine one more to that, then we're going to combine one more to that. So we have n rounds. So that's kind of what's adding to the complexity is that in the descending scenario, you have n cases, right? And the n cases has n rounds. So that's what gets us to n squared. But if we have this, then if we have this case that we have the runs which are n, we can't do much about that. But if we can shorten the rounds to log n, then our complexity would be n log n, which would be much better. So that's the idea is that we kind of want to like basically optimize merge all by basically merging them in pairwise brackets every time rather than one element at a time. And then for part E, implement your suggested change by refining one or both of these functions. Okay, so for this, basically what you would do is something like this. There's two approaches, a top-down approach or a bottom-up approach. So the top-down approach just basically takes the divide and conquer. What it does is we just write the merge all function of x's, and then we just combine, just do it by case. If it is null, then it's just a empty list. If there was just one element, because no tail x's means that there was just one element, then it would just be that element, right? And that otherwise, we would just do our typical divide and conquer approach, where we would have merge all ASS, merge all BSS, where ASS, BSS equals split at length of that thing of x's. So the idea is that we have the left-hand side, have the right-hand side. We're going to merge the two things together and then merge it together. So that's the divide and conquer approach. The bottom-up approach is basically using pairwise. So the idea behind this is that we're going to check the no excess is equal to empty, then there's just going to be empty. Otherwise, what we're going to do is we're going to take the head until null dot tail and then pairwise excess, where merge pairs excess is equal of this thing is equal to merge of AS BS of that merge pairs. CSS equals CSS. So this is just I'm defining merge pairs using kind of two things like pairwise matching. So if it was of this form, where I have AS, BS, CSS, then I would just basically do something where I merge the AS and BS, and then I combine it at the front of the merge pairs of CSS. So the idea is I merge the two pairs and I have the remainder of the parts. Otherwise, what I do is if there's only one, then I would just break it down into just that thing, right? There's not much to say about that. And then the head is just basically every time I'm just taking the head of the thing. And then my until function. My head is just basic. I want to explain this. Basically, the idea is that everything I do in this part, the until part to this part, is going to return a list of a nested list, right? And that ideally I stop when there's only one element. So that's when I stop. And if I want to stop and I need to return a type of just one list, then I would take the head so that it would just be the correct format and I would just return a list type. But over here, this one, because of the type, that's why I need the head, just to extract that part out. And then the until function basically just checks no.tail. No.tail basically means I'm up to one element, right? If no, like I take the tail of it and it's equal to no, then it means I have one thing left. And then the merge pairs is just the algo that I kind of continue going. Basically, I can kind of combine every pairwise thing together and merge it. And then the next one, I repeat the same process until I get down to one. So that's the idea. Okay, let's end off here.